Good morning, everyone. Thank you so much for coming here today and listening to me talk. It's such an honor to be in this great city, this great country. I mean, it's just so amazing to be here. But one of my biggest honors about giving these talks is I get the opportunity to represent 18,000 amazing women and men who make up the AMD engineering workforce. Everything I'm going to talk to you today about, it's their dreams. It's their ideas. These are not mine. These are all these people that work every day to make the greatest products in the planet. The title of the talk is Beating Moore's Law in an Interconnected World. Moore's Law, the fundamental observation that has really driven our industry. Dr. Gordon Moore, back in 1965, while he was at Fairchild, came up with an observation. Every year, we double transistors. Double the density of transistors. Well, he was an amazing man because he made a second observation. He didn't mind contradicting himself. He lived with the times. And in 1975, he came up with the same observation, but he changed it. We double our density of transistors every 2 years. And that stood the test of time for a very long time. And it was pretty amazing. It's what really drove my career when I started in 1985. And, unfortunately, every observation has its time. And if he were here today, he'd make a different set of observations because that was the man he was. The history of our industry is some way, it's governed by waves. Right? We've had a number of waves throughout history of compute. A relatively recent one in 1995, we had the web browser with the PC, and this was driven by Moore's Law, right? We were able to bring down the prices. We allowed more and more people to buy PCs. We provided an interface that changed society. It created social media, companies like Facebook, Google. It changed how people interacted. Over 400 million devices were sold a year at its peak. And then like any wave, it starts to crest some. And it was replaced by a second wave, again, driven by Moore's Law, right? This was the cell phone. The cell phone expanded the reach of computing yet again by changing the user interface, going to touch. Little children to very old people that couldn't use a PC now were able to go and interact with technology. But more importantly, it allowed people to communicate, share data, and that changed the world. I mean, it changed how people thought. It changed governments, it changed everything. And now we're at the next era, the HPC era. And this, again, is going to have a profound effect on everyone in this room and everyone on the planet. And it's the era of big data. It's the era of data center and AI, and using that big data to understand trends, to understand how we can use that data to answer questions, to create. It'll change how we think, it'll change how we work, it'll change how we interact. And that's the era we're in today, and AMD is very lucky because we're at the heart of the HPC era. We're in data center, we're in PC. We're in graphics and workstations. We're in edge computing. We're in adaptive computing through FPGAs. We're basically in every single part of this era. And AI is the center of our attention, and we're building AI machines that are so large they would barely fit into this room, down to AI machines that will be embedded in very edge client devices and making them smarter. So Gordon Moore, he's watching us today. Hopefully he's smiling. But his observation, it's changed. If we use his exact metric, things have slowed down. We're now getting double the density every 3 years. And even more importantly, we're doubling our efficiency, our performance per watt, in about 3.5+ years. And so things are getting harder. Our challenges are big. What's driving the lack of scaling is what we put on our silicon, right? Logic, NAND gates, NOR gates, inverters. We're doing a pretty good job. It's still scaling quite well. That only makes up maybe 60, 65% of the area of a typical SoC. We have to have storage, SRAM memory. That's not scaling well, right? That 6T cell, those feedback inverters, as we shrink and shrink and shrink, they become less stable. We're not allowed to bring voltages down. And so we can't shrink them as fast as the logic. Analog I/O, well, that's even worse. It's barely shrinking at all. When we look at its entirety, well, we've got a problem, and we've got problems to solve. But it's causing Moore's observation to basically extend out. So things, not only are they harder, we're going to have to start thinking differently. On top of it, every node is more complex. Whether it's building the machines that make the transistors, do the metallization, or coming up with the recipes to use those machines to create an entire fab line, it is harder and harder. It is much more complex. And then on top of it, costs are going up. In some cases, the cost per transistor isn't going down, it's leveling out. We've even seen some cases where it may increase a bit. And so, this is a pretty bleak picture. And I'm sure you guys all came here to smile today. And I didn't mean to bring out all these problems. But, we've got, magical people, we've got creative people, and they're called engineers. And the neat thing about engineers, the thing I love the most, is that you bring them the problems, they will solve the problems. And so we brought engineers these problems. And what engineers do is they innovate. And this is a very special word for all of us. And innovation isn't driven out of just, someone walking up and hitting someone in the back of the head and saying, think. No, innovation starts with competition. That's what's beautiful about all the companies that exist in the planet. And that competition, these problems, they drive desperation. So you start with competition, you get desperation, and then that desperation forces us to think, forces us to dream, and you get innovation. And thank God we have these engineers because they've started to solve some of these problems, right? For the longest time, we had planar transistors. We shrunk them, and they started to leak. We came up with high-K metal gate. We again shrunk and shrunk. They started to leak more. Well, a smart engineer put the transistor on its edge, wrapped the gate around it, created FinFET. Wrapping the gate created more surface area, gave us more control of that gate. Again, we knocked leakage down, we shrank, and once again, leakage hurt us. Then we came up with gate all around. This is the next big wave, right? We use nanosheets, multiple nanosheets. We again increase surface area, we get control, and trust me, as we look out, eventually we'll again run into the problems, and the engineers will have to innovate. So some of the problems, they're being solved. Now, this complexity cost issue, thank God we have wonderful companies that are working on the equipment. EUV, extreme ultraviolet, this is a key breakthrough for us. If we just take 7 nanometer and we look at immersion technology, we compare it to that same level of lithography, but using EUV, we not only reduce complexity, what took multiple mask steps, we can now do it in one. We can increase throughput, and just as important, we can increase yield. We get a 3% yield increase, which is amazing. So we're starting to beat these costs down. We're starting to improve flow through the production line. But we can't rely on our foundry partners, the equipment makers, device physics folks to solve the problem. Companies like AMD and others, we must step up and start thinking. And so architecture is a key piece of adding to this new version of Moore's Law, beating Moore's Law. AMD, way back in 2012, we were at a crossroads. I think if I asked any of you, would I be standing on stage today, you'd probably say no. We were in trouble. Well, our two leaders, Dr. Lisa Su, our CEO, and Mark Papermaster, our corporate CTO, they gave us 2 problems to solve. And it's very important they just gave us 2 because you get too many problems, you don't know how to prioritize. One, I'm sure you can guess. They said, create a CPU that we can use across many products, from data center to PCs to semi-custom gaming machines, game consoles, desktops, and that turned out to be Zen. And Zen was a game changer. It took 5 years, 500 engineers, over 1 million man-hours. It changed the trajectory of the company. But if I asked you the second technology they asked us to create, I don't think any of you would guess it. It was what we call the Infinity Fabric. What they asked us to do was come up with a way that would make it easier to build SoCs, faster, make it easier to verify, allow us to break out of a single chip and think multi-chip. And this is what we call the Infinity Fabric, and there's 2 pieces of it. One is a data plane, and we can tailor that data plane in various widths depending on the problem we're solving. Very small when we're trying to do a notebook, and it's very large when we're trying to do a supercomputer. And then just as importantly, we have a control plane that ties everything together, ties all of our power management, all of our control, how we do reset. I know reset sounds simple, but it's not. And the Infinity Fabric turned out to be, just as important, and maybe even more important than the Zen CPU, because it allowed us to design faster, quicker, and more importantly, start thinking of chiplets. How do you take big monolithic pieces of silicon and break them up and do it in a way where you can design it quickly, but more importantly, verify it quickly, and starting to think not just 2-dimensionally, but 3-dimensionally. And this really creates a leadership compute platform that we call the Infinity Architecture. We have many types of IP at AMD. We have CPUs, GPUs, fixed function, we have FPGAs, we have AIE engines, which are for inference, and they all get tied together with the Infinity Fabric. And this allowed us to start thinking 2D, 2.5D, 3D. It allowed us to take the new IP from our Xilinx acquisition and very quickly bring it into the AMD infrastructure. It allowed us to go and take new interface technology like CXL that allows for disaggregated memory, storage. Our competitors started 4 years earlier. We went into production before them, and it was all because of the Infinity Architecture. We could take these new concepts and hit the ground running. And now as we look at new interface technology like UCIe, which is going to change how third parties work with us, we can integrate their stuff in more easily, it'll again change things. Another key architecture piece is heterogeneous compute. Heterogeneous compute sounds simple. Whatever you're working on, put it on the right functional unit so you get the optimal performance and power. When you have an SoC with many, many types of functional units in them, we have CPUs, GPUs, AI engines, encode, decode, audio coprocessors, display. We have data processing units. We have security. We have camera ISPs. Well, that Infinity Fabric ties it all together with that control plane. And in the center is another microprocessor. We call it our system management unit. And as you interact with that machine, whether it's a large data center or a PC, that system management unit is watching what you're doing and turning everything off that we don't need, adjusting voltages up and down by dynamically monitoring all the voltages across the die, checking temperature all the way across the die, and basically orchestrating everything so that we have a full dynamic system. So heterogeneous compute sounds simple, but very difficult in practice. And that Infinity Fabric, that Infinity Architecture, truly enables it. SoC architecture goes along with this, because when we started to think about 2.5D and 3D, our CAD systems, they just weren't ready. It's not like you can go to Synopsys and say, give me an entire system. They have a lot of tools. We have a very large CAD methodology group at AMD, and as we think up solutions to the problems, we bring them to them so that they can help us architect a CAD system so our engineers can actually execute on it. Power optimizations are at the heart of what we're doing. Whether it's a battery power or a supercomputer, at the end of the day, they're both governed by the amount of power they use. It's amazing. The largest supercomputer is governed by the temperature of the HBM device at the bottom of the stack, where a PC, the length of movie playback, is again governed by how we can go and use that heterogeneous compute in the optimal way. And then system-level integration, what we put on our package, how we interact with what's off our package, voltage regulation, this all comes in. So these all work in concert in order to create this new version of Moore's Law. Now, the road to chiplets has been a long road. You know, in 2015, AMD with our partners, we developed the first product that used HBM memory. It was a 2.5D solution with a large interposer, 4 stacks of HBM, and a large graphics chip in the middle. We started this project back in 2007. It took us 8 years. We had multiple partners, SK Hynix on the HBM side, UMC on the interposer side. We had ASE helping us with the OSAT piece, putting it all together. It took all that time simply because it didn't take 8 years to design the graphics part or 8 years to just design the DRAM. It took 8 years to figure out how to assemble this, assemble it reliably, how to do the micro bumps for the stack of DRAM. SK Hynix had to work unbelievable amounts of time on it. But when we put it all together at the end, we didn't realize it, but we had a game-changing device. This HBM device that we first applied for graphics is now used in every high-performance system in the world. All of AI runs on HBM. It's a game-changing device that's now used by just about every company that participates, you know, in this latest era. 2017, we used the Infinity Fabric for the first time, and this was another problem that Lisa and Mark asked us to solve. When we started this project back in 2014, we didn't have a lot of money. And they were like, we want to get into data center, but whatever product we put in the data center, it's going to take a while for it to gain traction. We also need a desktop product, and we need a product that we can play in ultra-high-end desktop. Figure out how to design one chip and cover all these markets. Well, a few of us gathered together. We came up with the idea of building a single chip and then using the Infinity Fabric, when we have 4 of them, to connect it all together to become the first our first EPYC data center product. 32 CPU cores, 128 lanes of PCIe. It changed the TCO metrics in a major way. We put 2 down, and we created Threadripper, which is our workstation product, and we put 1 down, which created Ryzen, which is our desktop product. I mean, amazing leverage off a single chip. In 2019, we came out with our 2nd generation of EPYC. Here, we wanted to solve our I/O scaling issue. Remember, I/Os don't scale well. Well, the chip in the center there is a 14-nanometer chip, and it's surrounded by 4 7-nanometer chips. 7-nanometer at the time was very nascent. If we would have tried to build a large 7-nanometer die, we would not have yielded. It would have been costly. It would have been horrendous. We've seen people in the market try it. They failed. And so chiplets allowed us to deal with the costs of non-scaling I/O by using old technology and then using cutting-edge technology where it counted with the CPUs. And now, last year, the next big breakthrough, copper-to-copper hybrid bonding. 2 active pieces of silicon bonded together with copper pillars, and we did it with memory first, with SRAM, to double the size of our L3 caches for our data center products, as well as our desktop products. You can't go and stack something together for a cache that needs all that bandwidth if you want to use 3D microbumps. It's impossible. You just don't have enough connections. Well, our 3D V-cache, we partnered with TSMC. We worked together to go and prove out hybrid copper-to-copper bonding. And now we have products on the market that are actually active silicon, 3D stacked. This is not a PowerPoint slide. You could go buy these today. And then lastly, last year we came out with MI200. I'll talk a little bit more about this. But this uses, again, 2.5D technology, but with something we call the elevated fan-out bridge. You know, AMD developed this technology because, you know, with Fiji, that 2015 product, we had a very large silicon interposer. Now what we do is take small pieces of silicon, we place them on top of the organic substrate, and then we use that to connect to the HBM to give us that high-density connection, but without the massive cost of a big interposer. So lots and lots of change in this walking down the chiplet path. Hybrid bonding, I mean, it's an amazing technology. It's now flipping our mindset on how we think and how all of our products will be designed at some point. I'll talk about a special product that is real, that uses this in a very complex way. But copper-to-copper hybrid bonding is we take two pieces of silicon, we expose those copper pillars, we place them together, the dielectrics bond, and then with some temperature, we get the copper to fuse. The atoms flow in both directions. So we end up with a very, very small, very fine pitch, and very, and low loss, low resistance interface that we can basically use to now think 3D. And you get big, big benefits. The pitch is massive change, right? And as you shrink the pitch, we can now put transistors right near those copper pillars rather than using redistribution layers that consume a lot of power, right? By making everything short, everything small, everything tight, we're now able to get a 3x power improvement over what we could do with 3D microbumps. 3D V-cache, it took full advantage of this. If we tried to do this 2.5D, well, the copper-to-copper pillars, they give us a 200x increase in density. Over microbumps, a 15x increase in density. And then we get that 3x improvement in power. Amazing. Game-changing. I'm going to talk about a couple of products that you can actually go buy. We just announced this, just a few months ago. This is a desktop product called the Ryzen 7950 X3D. You can see there's two CPU die, and then there's a large I/O die. That I/O die is an older technology. The CPU die is in the latest 5-nanometer technology. And then one of them, we place a 3D copper-to-copper bonded SRAM on top of it. It doubles the cache size to 128 megabytes, and the results are phenomenal. If you're a gamer, this is the world's fastest gaming system now. And gamers, they only, they are the leading edge. They're the most amazing people. They come from all walks of life, and when they see this amount of performance increase, and we couldn't have designed a product with that big cache because the market is small, right? We're able to take an existing product, stack the cache, and then give, the folks that want it the most the highest performance. Another product we just came out with, we launched this, in the last, I think, September, October last year. This is the world's first chiplet gaming GPU. What we did here was attack both the SRAM scaling issue and the scaling issue we have with I/O. The chip in the center is 5-nanometer, and that's the graphics core. There's a little bit of I/O that comes off it, just the PCIe and display interfaces. Surrounding it, we have 6 memory cache die. This is where we put a large SRAM cache. So we're putting that in older technology because it doesn't scale. And then we're putting the vast majority I/O on that MCD die. That's the memory interface, the GDDR6 memory interface. It's a very large memory interface because it's very complicated. It's an asymmetrical SerDes. It was developed specifically to take advantage of DRAM technology with our DRAM partners from Samsung and SK Hynix. But we built it this way because we wanted to make it very cost-effective, but also give the absolute highest performance at the lowest power. And so we used our best transistors for the graphics compute. We use older transistors for SRAM and I/O. We get 61 teraflops of compute capability. But we had to solve another problem because we had to have cache bandwidth go between that MCD die and the GCD die. Not memory bandwidth, but cache bandwidth. So we had to develop a special I/O. And that I/O is very, very low power. It's designed for very, very short reach, but we get 5.3 terabytes per second of bandwidth. Unheard of on a chip-to-chip interface. When you aggregate it all together, 58 billion transistors, it's a game-changing product for gamers. We blew away our expectations, 54% improvement in perf power. We would not have been able to do this without chiplets. We would not have been able to do this without that ultra-low power, high-speed interface. We would not have been able to hit the cost if we didn't solve that SRAM scaling and I/O scaling issue. Now, MI200 is in the world's biggest supercomputer in the world today, the fastest. It's called Frontier. This machine is up and running. It was delivered last year. It's full operation. It's over 1.6 exaflop of capability. And that's all impressive all by itself. I mean, being the world's fastest is amazing. But what's even more amazing is it's the world's most efficient. Being fastest and most efficient, that rarely ever happens. Typically, most efficient is small. Right? You take advantage of a small area. Well, Frontier uses over 38,000 MI200s, around 300,000 HBM stacks. It's the size of 2 tennis courts. Barely, maybe it fits in this room. I mean, it's an amazing machine, and it's being used by data scientists to solve problems in weather, medical, used by the US Department of Energy to solve big, big problems that only Frontier can solve. I mean, it's a game-changing device, and you know, I have to say, every AMDer that worked on it, I was very lucky to be part of the team. I was very proud of it, and you know, Lisa always tells us, you know, you make great products, but you gotta beat your own products, and so we just announced this product, which is a follow-on to the MI200 series. It's called MI300. And this is by far the most complex product AMD has ever tried to build. We are now using 3D stacked copper-to-copper hybrid interconnect between not just active silicon, but silicon that is beyond memory. That's actually doing logic to logic. We have 4 base die in an older technology, and then on top of it, we have 9 chiplets that are either CPU or graphics compute that we stack on top of it. All hybrid bonding. Then next to it, we have 8 stacks of HBM. And then we use the Infinity Fabric to connect everything together in a vertically oriented way, because you have to have a lot of cross-sectional bandwidth. That top die may need the bottom die's memory. I mean, when I talk about the complexity everywhere along the path to achieve 146 billion transistors, I mean, the planning that goes is just crazy, because we don't naturally think 3D. When we put SRAM on top, we chose SRAM because it's very testable, repairable. You know, you can get known good die, but now we're using logic on logic. We had to go move the needle on known good die. We had to move the needle on test. We had to move the needle on all of our CAD tools. I mean, the level of change, and then we had to start thinking with our heads sideways, straight, backwards, because now it was a multidimensional world, which, you know, we weren't used to thinking in when it came to logic. So a lot of change, a lot of challenges, a lot of problems. But that's what I love about engineers, is they solve them. And you know, this, we fully intend to you know, be, again, the world's fastest. But if you look at the metrics, compared to MI200, we have 8x, almost an order of magnitude improvement in AI performance, a 5x improvement in performance per watt. I mean, Gordon Moore, when he's looking down, he's going, wow. Yeah, it's just all not about the process. Transistor density, now it's about a lot more. Architecture, 3D stacking, chiplets, we bring it all together. And we've got these 2 supercomputers. Frontier, as I said, is at Oak Ridge. It's in production. It's running. It's fully delivered. El Capitan is the next machine. We want to go faster than 2 exaflops. You know, we want to be the best in AI. We want to be the best in high-performance compute. We want to be the best not just in learning, but in inference. We want this machine to be, you know, the best in everything. And we'll see if we achieve it. We haven't completed it. This stuff is all working in the lab. So this is not slideware. This is not PowerPoint. This is fully up and running, MI300 in our labs. And hopefully, you know, the next time someone from AMD stands in front of you, they can talk about how we delivered El Capitan. And hopefully we can talk about, because we don't know. There's a lot of competition, but hopefully we can say it'll be the world's fastest. You know, so AMD, just to reiterate, you know, we're in cloud, we're in comms through Xilinx, we're a key part of 5G infrastructure. The work we're doing in AI, whether it's in these big supercomputers or putting AI into our smart client devices, our FPGAs, they're not just FPGAs, they have much embedded logic, so we call them adaptable systems. Gaming, it's my part I love. Simulation, virtualization, and then these smart client devices are going to allow you to interact with the cloud, allow you to interact with big data on your PCs and on your client devices. And so, today we're affecting billions at AMD. We know we're a citizen of the world. We look at every person in the world as someone we need to serve, and I could promise you, from the bottom of my heart, but more importantly, the bottom of every AMDer's heart, that we will work every day, every week, every month, every year to deliver all of you and deliver everyone in the world's greatest products that will change your lives and hopefully make the world a better place. Thank you.